Hey, it's me. I'm back for part 2 of the lesson. I know this is a long one today, but I think that this particular idea is going to be worth it. So sometimes when you're trying to factor something, look at this example. It has these numbers that have a lot of different factors, and you have so many things you could try. It's pretty discouraging. You don't just want to try everything and hope that you didn't miss anything. So there is a way to figure out if something is factorable without actually trying all the options, and it has to do with the discriminant. So imagine that this was part of an equation, even though it was just given as an expression. If it was part of an equation like this, and if you used the quadratic formula, and the part inside the radical, b squared minus 4ac, the discriminant, is there, if that number was a perfect square, then you could take the square root of it. You would just get something rational, so it would lead to a rational answer. And any quadratic equation that has rational answers actually was factorable. Now, if it's not a perfect square, then that tells you it's not going to be factorable because you have some other radical like square root 11 or square root 31 or something, and that is irrational or non-real if it's a negative. Okay, so let's check this one out. If we were finding b squared minus 4ac, that would be negative 19 squared minus 4 times 6 times 18. Let's figure out what that is. That's negative 71. That's not a perfect square, so we can conclude that this is not factorable, and we don't even have to try any of the possibilities. So I would tuck that little idea away and use it whenever it's convenient. If the discriminant is a perfect square, and that implies it's positive as well, then the quadratic expression is factorable. Okay, we're rounding off our lesson with some inequalities. So the only thing we need to consider here that's any different from what we were just doing with the equations is that we would have a solid or dotted depending on the inequality sign, and we would have shading either inside or outside the parabola. So first let's consider y equals 2x squared minus 7x plus 4. That's going to be the parabola. I'm going to change this to vertex form, so here's a reminder of how you can do that. You can factor the 2 out of the x squared term and the x term. Leave a space. I'm going to complete the square. Half of negative 7 halves is negative 7 fourths. Square that, and we get 49 sixteenths. So that's what's added in here, but really remember we multiply it by 2, so we need to subtract 2 times 49 sixteenths, and that's 49 eighths to keep things balanced. So we can now write this as y equals 2 times the quantity x minus 7 fourths squared plus, well, let's see, 4 over 1 is the same as 32 over 8. So those are going to add together to be minus 17 eighths. Okay, so not the most user-friendly numbers in the world. The vertex is 7 fourths, negative 17 eighths. So that would be 1 3/4, negative 2 1/8. So I'm just going to make a rough sketch just for the sake of time. We know it opens up. We have that vertex. I'm going to make this really, really rough. I hope you don't mind too much. But just to get the point across, so here's our vertex. We know our y-intercept is at 4. Let's pretend that's 4. We know it opens up. So now what I want to do is because this is a greater than, without an equal to on it, I just want to make this dotted. And if I was doing this for real, taking more time, I would find the x-intercepts and so on. Now we want to find out whether to shade inside or outside. So let's test the point 0, 0 into our inequality. 0 is greater than 2 times 0 squared minus 7 times 0 plus 4. So 0 is greater than 4 is false. So we don't shade 0, 0. So that means we are going to shade inside. Okay? So that puts together some ideas from this chapter as well as the last. And then finally, how about putting together even more ideas? Suppose we have a system of quadratic inequalities. So we have two different parabolas, dotted or solid and shaded, and we want to see where the shading overlaps. So this one right here is actually from an equation we used earlier. If I change it into an equation, you might recall that we had to use the quadratic formula on that. And so to find the x-intercepts, I set that equal to 0. I divided both sides by -2, and we found out that there was just a single x-intercept. It was x equals -1. Oops, sorry, sign error. It was x equals +1, and that was also the vertex. So the vertex was at 1, what was the rest of it? 1, 0, yeah. Okay, and then this one here, it's just your regular parabola y equals x squared, but shifted down 3. So once again, just for the sake of time, I'm going to make this kind of quick, just to get the idea across. Hopefully going by ones is going to be fine. Okay, so I'm going to do the first one in purple. Y equals x squared minus 3. Vertex would be down here at 0, -3, over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4. Dotted, because it's just a greater than, not a greater than or equal to. And when you test 0, 0, 0 is greater than 0 squared minus 3. 0 is greater than -3 is true. So we would shade that one inside. Let's just hold off on that for the moment. Actually, no, I'll go ahead. I'll just use 2 different colors of crayon. We should be able to understand what's going on when we get there. Okay, now for the second one, do this one in green. Vertex at 1, 0. It opens down. Y-intercept is -2. And this one's going to be solid because it has an equals to, a less than or equals to. So something like that. And then let's check 0, 0. 0 is less than or equal to -2 times 0 squared plus 4 times 0 minus 2. 0 is less than or equal to -2 is false. So we're not going to shade 0, 0. We're going to shade the other way, which means here. So what I'm seeing is that the overlapping shading is that little kind of kidney bean in there. Okay, so we've been able to combine a lot of big ideas in this lesson. I hope it was as fun for you as it was for me. And here we have the quadratic formula stuff from section 4.8, and I did sneak in the inequalities from section 4.9. Thanks, everybody.